Hey everyone! Welcome back to Education is Life, your go-to channel for unlocking the wonders of learning. It is me, Joe Edgo, and today we're diving into Lesson 3 of our Arduino UNO R4 Minima Ultimate Training Series, focusing on the basic circuits and breadboarding. In this lesson, you'll identify the components of an electrical circuit, understand the different types of circuits and how they are represented in diagrams. You'll learn the relationships between current, voltage, and resistance as expressed by Ohm's law. And finally, you'll be able to practically apply this knowledge by building simple circuits using LEDs, resistors, connecting wires, and your Arduino UNO R4 Minima on the breadboard. As always, I'd like to give a special thanks to SunFounder for sponsoring this course and making this learning journey possible for all of us, especially for beginners. And this Arduino UNO R4 Minima Ultimate Training Sensor Kit is sponsored by SunFounder, will be our trusty companion throughout this course. So, if you are still looking for materials that can best guide you in this all-new Arduino UNO R4 adventure, I encourage you to please check this one out. You'll find this on Amazon and on the official SunFounder website. The links are in the description below. So now, let's start building circuits. For this hands-on learning session, you'll need the following materials: a breadboard, 3 LEDs, a number of resistors with values ranging from 220 ohms up to 10 kilo ohms, connecting wires, a 9-volt battery with battery cap, and your Arduino UNO R4 Minima. In general, a basic electronic circuit is made up of at least 3 main components. First is the power supply or a voltage source that provides the electrical energy necessary to drive the circuit. It can be a battery, an AC adapter, or other sources. Second is the load that converts this electric potential energy to another form. A bulb is a good example of an electric load that converts electric potential energy to light and heat energies. A resistor is another example of an electric load that limits the flow of electric current in an electronic circuit. And finally, conductors. Conductors provide pathways for electrical signals to flow through the circuit, such as connecting wires that are used to connect the load to the power source. The most basic, yet most important law of electric circuits is Ohm's law. Ohm's law explains how voltage, current, and resistance are all related. To help you understand this concept, consider this analogy: an elevated water tank with water flowing through a water pipe. Now, think of voltage as analogous to water pressure. As the tank's position gets higher relative to the ground, the water pressure increases, and this works similarly to voltage. A voltage is simply the distance between 2 points. For example, when we say something has 5 volts, what we mean is that it has 5 volts compared to the 0 volts, which is the ground. Now, the current is analogous to the amount of water flowing through the pipe and is measured in ampere. When more pressure is applied, then more water will flow through the pipe. That is, when more voltage is applied, more current will flow. Now, the third variable in Ohm's law is resistance. This is analogous to the size of the water pipe. Squeezing the water pipe is like increasing the resistance, limiting the amount of water or current flowing through it. With this simple illustration, Ohm's law can be written using the following equation: voltage equals current times resistance. The same formula can be rewritten in order to calculate current and resistance respectively as follows: current equals voltage divided by resistance, and resistance equals voltage divided by current. Now, let's take a look at the simplest circuit possible, consisting of a voltage source and a resistor. A resistor, as its name suggests, is a passive electrical component that resists the flow of electrical current. The amount of resistance is measured in ohms. Assuming the voltage source is 5 volts and the resistor value is 1 kilo ohm, so how much current will flow in the circuit? By using the formula, current equals voltage divided by resistance, we have 5 volts divided by 1000 ohms equals 0.005 amperes or 5 milliamperes. Now, if I change the voltage source, increasing it to 9 volts, but the resistor value remains 1 kilo ohm, how much current will flow in the circuit? By using the same formula, current equals voltage divided by resistance, we have 9 volts divided by 1000 ohms equals 0.009 amperes or 9 milliamperes. This tells us that the current flowing through a circuit is directly proportional to the voltage. When more voltage is applied, more current will flow, like the water tank analogy. Please note that you might see some circuit diagrams illustrating the current flows from the positive terminal through the circuit and into the negative terminal. This is known as conventional flow, which is commonly used by engineers in their circuit diagrams. However, some diagrams will illustrate that electron flows from the negative terminal, through the circuit, and into the positive terminal. This is known as the electron flow, which is the actual flow of current. Either way, both notations are widely acceptable, and it does not affect the actual values of your electric components. So now, if we're going to implement this given circuit diagram using actual electric components like battery, connecting wires, and resistors to perform experiments and prototyping, we need to learn how to use a breadboard. A breadboard is an essential tool in the world of electronics, used for prototyping circuits without the need for soldering. Its grid of interconnected holes allows for easy placement and connection of electronic components. Both sides of the breadboard are called power rails. Usually, they have the markings of negative and positive, or color coding, that serve as a guide. Note that these markings and color codes serve only as a point of reference, although there is no rule requiring you to connect the ground to the negative rail and power to the positive rail. It's best practice to keep things organized so you don't get confused. Now, most breadboards have power rails that are connected vertically from end to end, although you must know that there are some breadboards with power rails that are disconnected in the middle. Also, it is important for you to be aware that the power rails on both sides are not electrically connected. So, if you want the same power source on both sides, you will need to connect the two sides with some jumper wires like this. Now, these horizontal rows of the breadboard are called terminals. You'll notice that there are also markings on the sides, such as letters, numbers, or symbols. And the way these markings are laid out may vary from breadboard to breadboard, but the purpose is all the same. These markings help you locate the exact holes you need to connect the components to, like locating a cell in a spreadsheet. For example, B5 refers to this hole, column B, row 5. Unlike the power rails, which are internally connected vertically, terminal strips are internally connected horizontally. Each row has 10 holes, but only up to 5 components can be connected on either sides. It is because there is a division or a ravine in the middle of the breadboard. This ravine isolates both sides of the given row from one another, and they are not internally connected. This ravine allows the placement of integrated circuits or ICs that come in dual inline package or DIP. In effect, you can connect components to each side of the IC without interfering with the functionality of the leg on the opposite side. So now, let's implement our previous resistor circuit to start experimenting with Ohm's law. I'll use this 9-volt battery and a battery cap to connect the positive terminal of this battery to the positive rail of the breadboard. The same goes for the negative terminal. And then, I'll place one leg of the resistor to, let's say, row 10, but regardless of the column, because recall that they are internally connected. And then, the other leg can be placed in any row except row 10. Because if you connect the other leg of your resistor to the same row, it will be short-circuited. This will cause the resistance to decrease as both legs touch each other. In effect, excessive current will flow through the circuit as resistance nearly becomes zero. This may cause damage to your electronic components that are connected to the circuit. Now, to complete the circuit, we need to connect both legs of the resistors to the power source. Note that resistors have no polarity. Current passes equally through from either direction. Thus, you can use both legs interchangeably. Note that there are countless ways we can implement this circuit diagram. We can do this, or this. And you can implement your own circuit connections the way you want them to. Now, there are two main types of electric circuits based on the way components are arranged: the series and the parallel circuits. In series circuits, loads are connected like a chain. Consider this given diagram where the second resistor begins where the first one ends, and then the third resistor begins where the second one ends, and all the way back to the power source. So, let's implement this circuit to the breadboard. There are principles that you need to learn when implementing a series circuit connection. The first principle states that the sum of the individual voltage drops is equal to the total supplied voltage. For this example, this battery as our voltage source, when measured using a voltmeter, has a value of 9.35 volts. So if I measure these individual voltages across each resistor, like in this 10 kilo ohm resistor, the voltage drop is 8.33 volts. In the 1 kilo ohm resistor, the voltage drop is 0.83 volts or 830 millivolts. And for this 220 ohm resistor, the voltage drop is 183.2 millivolts. Now, if we add these three individual voltages, the total is 9.35 volts, which is equal to the total supplied voltage of this battery. Now, the second principle states that the total resistance of any series circuit is equal to the sum of the individual resistances. Since I have 10 kilo ohms, 1 kilo ohm, and 220 ohm resistors connected in series, the total resistance should be 11.22 kilo ohms. To verify this, I'll disconnect my battery first and then tap the probe of this multimeter on both ends of this resistor in series. So I can read 11.22 kilo ohms, which validates our second principle. The third principle states that the amount of current that flows in a series circuit is the same through any components. And this is an advantage of this type of circuit connection. The same amount of electric current flows through all components. By using Ohm's law, current equals voltage divided by resistance, we simply divide 9.35 volts by 11.22 kilo ohms. The total current is 0.833 milliamperes. And according to the third principle in a series circuit, we know that 0.833 milliamperes is the same electric current flowing through all the components. So technically, we don't even need this multimeter to know the individual voltage drops across each resistor, because we can simply compute them using the formula voltage equals current times resistance. For example, the voltage drop on this 10 kilo ohm resistor is 8.33 volts. For this 1 kilo ohm resistor, the voltage drop is 0.83 volts. And for this 220 ohm resistor, the voltage drop is 0.183 volts. And we know that these individual voltage drops, when added, will result to the total supplied voltage, which is 9.35 volts. That's why a series circuit is commonly known as a voltage divider circuit, as the total voltage is subdivided into the individual components in the series circuit. In parallel circuits, components are connected in branch pathways, as represented by these three resistors as our example. Each component of the electrical circuit is connected from both ends of the component directly to the source of electricity, creating its own loop. Each place where a loop branches off is called a node. The current flows from the voltage source through the nodes to each component and then back to the source. So, a portion of the current is flowing through all the components at the same time, because each branch is independent of the others. If there is a break in one of the branches, it will not affect the other circuit components in the other branch. Unlike in a series circuit, wherein the components are connected in consecutive ways, one after another, creating a one big loop for the current to flow. In effect, if one component is burnt, the entire series circuit is opened and cannot work. Now, let's implement this given parallel circuit based on this diagram to understand how it works. So, I'll connect these three resistors in parallel like this. Then we have a 9-volt battery as a source. So, I'll connect the positive terminal of this battery to this node and the negative terminal of this to the other node. Now, the principle in a parallel circuit are as follows. First, the voltage across all components in a parallel circuit is equal. We can verify this using a voltmeter and measure the individual voltages across each resistor. And as you can see, regardless of the resistor's value, the voltage across is the same. The second principle is that the total resistance in a parallel circuit is smaller than the value of the smallest individual resistance. Recall that in a series circuit, individual resistances are added to get the total resistance. However, in a parallel circuit, we compute it differently. Notice that if I measure the resistance across these three resistors, I am only reading roughly 177 ohms, even though I have 10 kilo ohms, 1 kilo ohm, and 220 ohms resistors in this circuit. But according to the second principle of parallel circuit, the total resistance is diminished to a value that is smaller than the smallest resistance. In this case, the smallest is 220 ohms. We can actually compute it using this formula. Total resistance equals 1 over quantity 1 over R1 plus quantity 1 over R2 plus quantity 1 over R3. And substituting the values of the resistors, 10K, 1K, and 220 ohms, the total resistance is computed as 177.13 ohms. This is very close to what we've measured. Well, it's not exactly the same because the actual values of the three resistors are not exactly 10 kilo ohms, 1 kilo ohm, and 220 ohms. They are off by a few ohms plus or minus. Finally, the third principle states that the total current is equal to the sum of the individual branch currents. It means that in a parallel circuit, the current is being subdivided instead of the voltage. That is why it is commonly referred to as the current divider circuit. So, if we want to know the total current of the entire circuit, we can compute it using the same formula. Current equals voltage divided by resistance. So 9 volts divided by 177.13 ohms equals 50.81 milliamperes. Also, to get the individual current that flows through each branch, we use the same formula. Current equals voltage divided by resistance. So the current that flows through this 10 kilo ohm resistor is 9 volts divided by 10,000 ohms equals 0.9 milliamperes. The current that flows through this 1 kilo ohm resistor is 9 volts divided by 1000 ohms equals 9 milliamperes. And finally, the current that flows through this 220 ohm resistor is 9 volts divided by 220 ohms equals 40.91 milliamperes. Thus, adding these three individual branch currents will produce a total current of 50.81 milliamperes. All throughout this course, we will be implementing series and parallel circuits as we learn different components that we will be incorporating in our projects. So, This is a good start to learn the basics of circuits and develop your skills along the way. The first example where we can apply this knowledge right away is when connecting an LED to any of the digital I/O pins of our Arduino UNO board. First, let's implement this circuit as shown in the diagram. In here, pin 2 of the Arduino board will be our voltage source. If we have a simple program like this, we configure pin 2 as digital output pin, then send logic high to this pin using the digital write function. Arduino will produce an output voltage of up to 5 volts at pin 2. Then, a 1 kilo ohm resistor is connected in series with an LED. By the way, the LED symbol is the standard symbol for a diode, with the addition of 2 small arrows denoting the emission of light. The positive side of the LED is called the anode, and it is marked by having a longer leg. The shorter leg denotes the negative side of the LED, and is called the cathode. An LED or light-emitting diode is a special type of diode that emits photon light when an electric current flows through it. Well, a diode is a type of semiconductor device, and the most common function of a diode is it allows current to only flow in one direction. And for a light-emitting diode, when there is no current flow, there's no light. Current flows from the anode to the cathode and never in the opposite direction. So, connecting an LED in reverse can keep an entire circuit from operating properly by blocking the current flow. So, don't worry if reversing an LED breaks your circuit connection. It won't damage your LED or your Arduino board. Also, it doesn't matter if a resistor is placed before or after an LED. It will still work the same. This resistor reduces the current flowing through this branch. Now, the biggest question to ask is, how do we determine the appropriate resistor value to use when connecting an LED to the Arduino pin? To answer this, we need to know 2 important information. The maximum output current your Arduino UNO R4 board can produce per digital pin, and the maximum forward voltage and current ratings of your LED. Yes, LEDs have their own voltage and current ratings. Depending on your LED size and color, this information may vary. In this example, I can use a multimeter to measure the voltage drop across this LED, and it reads 1.83 volts. However, the voltage drop across this resistor is 2.88 volts. Recall that in the series circuit, the sum of the individual voltage drops amounts to the total voltage supplied to the circuit, and this is equal to 4.71 volts. So now, how do we compute the ideal resistor value that we should use? For example, a common 5mm red LED has a forward voltage of about 1.8 to 2.2 volts, with a maximum forward current of 20 milliamperes. Using the same formula in Ohm's law, resistance equals voltage divided by current. If we know the forward voltage rating of the LED that we're using, say 2.2 volts, and we are drawing power from an Arduino pin that outputs 5 volts ideally, then the voltage drop across this resistor is 5 volts minus 2.2 volts equals 2.8 volts. Now, what about the current? This 5mm red LED that we're using has a maximum forward current rating of 20 milliamperes. It means that we can give it 20 milliampere or less, and it will shine its brightest at 20 milliamperes. Recall that the amount of current that flows in a series circuit is the same through any components. Now, here is the catch. According to the technical specs of the new Arduino UNO R4 series, the maximum current draw per GPIO is 8 milliamperes, which is significantly lower than previous versions, and exceeding this limit may damage your pin or board. Note that the older UNO R3 has a maximum current rating of 40 milliamperes or 20 milliamperes continuous current. So it means we cannot use the 20 milliampere current rating for computing the appropriate resistor value when using the UNO R4 Minima. So, to get the resistance value, we divide 2.8 volts by 8 milliamperes only. This gives us 350 ohms. Well, this is the resistance for the maximum current drawn of 8 milliamperes. And just to be safe, I'll limit the current draw to only 4 milliampere. So, 2.8 volts divided by 0.004 amperes equals 700 ohms. Well, for most LEDs, 4 milliamperes is enough for it to light. If we are just using it as a LED indicator, if you don't have an exact resistor value of 700 ohms, you can use any value that is close to this. For example, I'm using a 1 kilo ohm resistor for this circuit to limit the current that flows through this LED. Now, I encourage you to try and experiment with different resistor values that limit the amount of current flowing through the LED. Say, a 10 kilo ohm resistor, you will notice that the LED's brightness is way dimmer. And if I change this resistor one more time with a much smaller value, the LED's brightness is way brighter. It means that more current is flowing. So, what can we conclude? Using a higher resistor value limits the current that flows through the LED, thereby reducing the brightness of the light that it emits. However, using a lower resistor value allows more current to flow through the circuit, thereby increasing the brightness of the light the LED emits. For your challenge activity, choose 3 GPIOs on your Arduino UNO board and connect the 3 LEDs using different resistors per LED. This should produce different brightness levels. To practice your previous programming skills, write a program that turns on these LEDs one after the other and then loops repeatedly. Again, thank you for joining me in this lesson on basic circuits and breadboarding, where we explored Ohm's law, series and parallel circuits, and their applications using the Arduino UNO R4 Minima. For our succeeding lessons, we'll continue learning the various Arduino programming constructs, understanding variables and conditions, and learn how to properly read digital input signals from your Arduino board. If you found this lesson enlightening, don't forget to hit that like button, subscribe for more knowledge-packed sessions, and ring the bell to stay updated. So, keep learning, keep experimenting, and always remember, education is life. See you in our next lesson. Happy coding!